For the first problem, I chose the fast doubling Fibonacci sequence. It is one of the fastest algorithms for Fibonacci ever. Its complexity, big O notation, is log of n, meaning that it is so fast and very useful. Also, I looked up its formulas. Um, as usually, it starts with 1, 1, but doubles each number. So each time it skips a few numbers and goes until it reaches the needed number. By that, it does a few steps in one. Okay, so for the second problem, I chose two algorithms. Fast doubling, which I described in for the first problem, and also the Binet's algorithm. And I chose Binet's algorithm because it's very unique compared to the others because it doesn't use any loops or recursion. It just uses math, nothing else. And here's its equation. It's a little bit so here's the parent code. No, fast doubling uses a recursion, so it has two functions. The first step is it checks if n is equal to 0, then it returns 0. Uh, I have two numbers because I have two formulas, so I need for 2n and for 2n plus 1. And then it uses the formula by here it uses the recursion, uh, and then it just finds the number by multiplying and subtracting them. Then it again returns two numbers, but at the end it just takes the first. And this algorithm is super fast. But with Binet's formula, it is a bit different because here it just uses mm, it has the same first step. If n is less or equal to 0, it returns 0. Then it just uses the formulas, which I showed before, and then it rounds it up. And okay, so for the third problem, I chose um fast doubling algorithm. Oh, I chose it because I also wanted to look just how it looks and how the numbers it gets, and increased n by 100. And after after I got all the numbers, I noticed that they get bigger just by 21 each time. And of course, I divided by 100, and its slope is just 0.21. As you can see on the graph, it is just a straight line. Okay, so for the problem number 4, the first algorithm I used was the fast doubling. It used the recursion, and I calculated its time, and it was big O notation of log n. It is pretty fast. It is not linear. It is exponential. So it's super fast and so universal. And as I thought, as I thought, it will be just a very slow increasing clock because it's super fast. I checked it and it runs like in less than a second, and I liked it. And then I also looked up for the Binance algorithm, and based on its formulas and code, I just I think its complexity because notation is just one because no loops, no recursion, just many functions. And I like it, but it's not that fast because the fast doubling is it is a bit less than 0. Okay, so then I ran the code with random numbers, and I found out that it it's exponential, but it's not that fast. As you can see, it gets uh, up, but with some as well. Okay, here's the code. I used the same function for fast doubling, and also I used this function to find the time. I didn't use the same one as it was given because when I use without this perf counter, it almost all the time it just gave me 0 0 for all the inputs. But this function makes it doesn't round it up. So yeah, after for example, I have 3 point something. After point, there are so many numbers, and this makes it's right. For example, if I will run it, it gives me, as you can see, so many numbers. And by these numbers, I already made the table.